What I'm going to do now is move on to another group of tools, the resistivity sensors. We have several of these. Again, there are differences between different tool types which you need to understand, and I'll take you through each one and show you how they differ from each other and how that affects the data that you will get on the logs. Today we have three basic designs of resistivity sensor that we use. We have the EWR phase 4. EWR stands for electromagnetic wave resistivity. That tool's been around for quite some time now and is in fact being retired from the fleet, although we do still have quite a large number of those tools around. A more recent design is the EWR M5. This is the one that has the AGR, azimuthal gamma ray sensor, built into it that I was talking about earlier. This has a similar design to the original phase 4, except that it has more spacings and more frequencies, and I'll get into the details of those in a little bit. The third tool is the ADR, the azimuthal deep resistivity, which is essentially an azimuthal version of the M5 with a few differences, which I'll also take you through. You can see from that one that it has these tilted antennas rather than having perpendicular antennas like the other two tools, and that tilt is what gives the tool its azimuthal sensitivity. That's the one we use mostly for geosteering these days, in high angle and horizontal wells. Most of the geosteering we do now is done with the ADR sensor. All three of those tools work on pretty much the same basic principle. We have two methods that people talk about for measuring the resistivity of the formation. One is referred to as a phase shift resistivity, and the other is attenuation resistivity. And you'll see those in curve labels and on log plots as two different curves or sets of curves that you might encounter on a plot. So I'll just explain what the difference is between those two. The tools all work in roughly the same way. We have at least one transmitter on the tool and a pair of receivers. The transmitter puts out a radio wave. We have various frequencies that we use, anything from as high as 2 megahertz down to 125 kilohertz, depending on the tool that we're talking about. But it radiates this wave out into the formation, which is detected by the two receivers, which are further down the tool here. By the time it's reached the receivers, two things really happen to it. One is that it gets attenuated. You can see that the amplitude of this wave, which arrives at the first receiver, R1, is higher than the amplitude at R2. That's because the signal, as it's traveled that extra distance, has been attenuated some by the formation. And the degree of attenuation, the amount of attenuation that happens in that interval, is a function of the formation resistivity. So by measuring that change, in fact, what we do is we take the ratio, the amplitude ratio between these two signals, and then we can calculate from that what the resistivity of the formation was in that interval. The other thing that changes is the phase. You notice that the wave at R2 is slightly shifted to the right compared with the wave at R1. That's simply because it takes longer for the wave to get there than it does to get to R1. So there's actually a time delay. Now, we're talking about the speed of light, or something like approaching the speed of light here, so the actual time is extremely small. The time difference between these two is very small. So rather than try to measure that, what we do is we measure the phase of the two waves relative to one another. The amount of phase shift that we see is illustrated in this plot. That phase shift between the two, between R1 and R2, is also a function of the resistivity of the formation. The more resistive it is, the smaller that phase shift becomes. It never gets to zero because there's always some time delay between these two, but as the resistivity decreases, if the conductivity increases, then these move apart, and based on a measurement of that phase shift we can calculate the resistivity. So we have two ways to get resistivity out of basically the same measurement. We take the amplitude ratio and we take the phase shift. Now, of those two, the phase shift measurement is considered to be the preferred measurement. There are several reasons for that. One is that it has a broader range of operation in terms of resistivity values that can be measured. The attenuation resistivity tends to max out at around 10 or 20 ohm meters, whereas the phase shift resistivity can go up to several thousand ohm meters. A lot of reservoirs are in that upper range, and using attenuation measurements in those reservoirs doesn't really work. So we use the phase shift because of its broad operating range. It also tends to have a somewhat better vertical resolution in terms of how well it can distinguish between thin beds. There are one or two other benefits to do with dielectric sensitivities in the formation. Besides resistivity, there are also dielectric properties of the formation which interfere with the measurements, and the phase shift measurement is less sensitive to those than the attenuation. On the other hand, the phase shift resistivity doesn't have as great a depth of investigation. You can see the cartoon on the right here illustrates that the amplitude ratio measurements effectively see deeper into the formation than the phase shift measurements do. That's kind of counterintuitive. How can one measurement be different from the other when they're basically the same wave that we're talking about? This is one of those things that we just have to accept as a fact of life, that in fact the attenuation data does tend to see or be sensitive to changes further away from the tool than the phase shift resistivity. The physics of that is horrible, and I'm not going to try and explain it here. Now, there are several environmental effects which can have an impact on our resistivity measurements. The borehole fluid, for example, in the wellbore, the mud that fills the borehole, has an impact on the resistivity measurement. The tool is basically measuring all of the surrounding materials that it finds itself in, whether it's borehole or formation. They both impact the measurement. So we have to take steps to compensate for the effect of the borehole in order to get the true resistivity of the formation. Bed boundaries can also have an impact. I'll talk a bit more about how that works. When we're close to bed boundaries, the measurements can become distorted, and we need to watch out for that and be aware that that could be happening. Fractures also can interfere with resistivity measurements. We're basically talking about electrical currents flowing through the formation, so fractures tend to get in the way and interfere with those currents. Tool eccentricity is also a factor. In some situations, if the tool is off-center, that can distort the measurement as well as invasion. Invasion of fluids from the borehole into the formation also affect the measurement, so that shallower reading measurements are more affected by the invasion than the deeper reading ones are. And finally, anisotropy, which is a property of the formation where the resistivity is different depending on which direction you measure it in. That typically comes into play where we have thinly laminated formations, where the resistivity parallel to the bedding planes is generally lower than the resistivity perpendicular to the bedding planes. And the tool is sensitive to both of those things, and we have to look out for that in those kinds of situations as well. So taking each of those effects in turn, if we start by looking at the effects of the borehole fluid, this is a picture which illustrates the tool inside the borehole. We have the rock that we're drilling through. We have the mud which fills the borehole. We have the tool here, which of course has a hole through the middle for the mud flow down the center. The tool effectively generates electrical currents which flow around it. Sometimes it's convenient to think of this as a wave traveling through the formation. Other times it's convenient to think of currents. The two things kind of go together. In this case, it's useful to think of it in terms of current flow. So around the tool, we're generating current loops, which basically travel through the formation like this. It's actually an alternating current. It's not just in one direction. It goes back and forth at whatever frequency the tool is firing at. But just for illustration purposes, I've shown it in one direction. And of course, some of that current also flows in the mud. So you can think of this as like an electrical circuit where we have two parallel circuits, some of the current is flowing through the mud, some of the current is flowing in the formation. So the total signal consists of a bit of both, and we have to subtract out the signal which comes from just the mud to leave us with the signal that's just from the formation. This screenshot is from the eChart book, which I was showing you earlier for the gamma ray borehole corrections. It also has functionality for the resistivity borehole corrections. The borehole correction is basically driven by two things. You need to know the borehole diameter and the resistivity of the fluid in the borehole, so the mud resistivity. This is where it's important for our field engineers to actually go and measure what that is. One or two of our tools do actually have sensors on them which measure that directly, but most of the time they have to measure it manually using a meter at surface. So if you know what the borehole diameter is, we can put that in here. We can know what the mud resistivity is at the downhole temperature. It's important to remember that the mud resistivity changes with temperature. So if you measure it at surface with a meter, that will be at room temperature. Downhole is going to be a lot hotter, which will in general mean that the resistivity of the mud is lower downhole than it is at surface. So we have some extra math to do to come up with this figure that we put in here. This is illustrating for the phase 4. We have other charts for the other tools. It also requires selection of a particular spacing. This is the distance from the transmitters to the receivers. We have multiple spacings on all of our tools, so you need to be careful to select the one that you're looking for, and whether or not it's a phase measurement or an attenuation measurement. Having put in these two parameters for the mud properties, you can also select a raw uncorrected resistivity value. In this case we've picked 5 ohm meters. And when you hit the button, it calculates what the corrected value is. So that would be the resistivity value of the formation with the borehole effect taken out. That's illustrated on the right hand side on this chart, where the correction factor is shown on the vertical axis as a function of formation apparent resistivity. So this is the raw measurement that the tool makes. The actual correction varies with resistivity, so it's not as simple as it was with the gamma ray case. This is more complex. But on here you have a red line which shows the selected hole diameter. You can see how the correction changes with resistivity, and you also have other hole sizes on here. So you can see that by increasing the hole size from say 10 inches to 11 inches, you make a pretty dramatic change in the correction factor. In fact, it just goes off the chart just there. So hole size makes a significant impact on some of our measurements. This 9-inch measurement is the shallowest measurement on the phase 4 tool, and because it's the shallowest, it's also the most sensitive to the borehole effects. If you look at similar charts for deeper spacings or longer spacings, those are less sensitive to the borehole effects and won't have such dramatic correction factors. The magnitude of the effect that we see on the resistivity measurements depends on several things. It depends on the size of the hole. The bigger the hole, the bigger the effect. It depends on the mud resistivity, and the lower the mud resistivity, the bigger the effect on our measurements. And it also depends on the depth of investigation of the individual measurements. All of our tools have multiple depths of investigation, and the ones which read the shallowest are the most affected by the borehole, as you might expect. Here I've got an example from a 12¼ inch hole filled with mud which is pretty low resistivity, 0.06 ohm meters. And the log is from an EWR phase 4 tool. This would be an 8-inch tool in this hole size. On the right you can see the 4 measurements from that tool. The blue curve is the shallowest and the red is the deepest. I'll get into the details of the tool and how it's constructed later on. On the left we've got some caliper data showing that we have some intervals which are fairly well engaged and other intervals which are washed out. The formation is quite homogeneous. It looks like a shale. It's quite high gamma ray. And the red curve here is the rate of penetration on a reversed scale, showing us how fast we're logging. Don't worry too much about the scales on this particular example. You can see that the effect that the borehole has on the log is greatest on the shallowest spacing, where it's reading significantly lower than the deeper spacing. The borehole effect tends to make measurements read low in general, and it's the shallowest ones which are the most affected. Down here, you can see that the effect is increased. All of the measurements read a little low in this area where there's larger borehole, and particularly the shallowest measurement, the 9-inch resistivity, which goes very low relative to the others. This kind of spread that you see on these between these curves could be due to other effects. In particular, it could be due to invasion or anisotropy, both of which I'll talk to you about later on. But in fact, we know that since we're in a shale, we're not expecting any invasion, and this was a near vertical well, so we don't expect to see any kind of anisotropic effects. So really the only thing that explains this is a borehole effect. What's happening is that the shallowest spacings are being strongly influenced by the mud in the borehole, whereas the deeper spacings probably aren't. We can correct for this, of course, with our borehole corrections, which I showed you just now. This is an illustration of what happens when the tool encounters a boundary. Here we've got two different rocks, rock 1 and rock 2, which have different resistivities. The boundary between them intersects the borehole. We have the tool centralized in the borehole as we did before. The tool is going to generate electrical currents which will flow around the tool like this in the formation. But in doing so, they have to cross the boundary. They cross it in two different places on opposite sides of the borehole. And when that happens, you get an accumulation of charge. You can think of this as somewhat like a capacitor in an electrical circuit. The charge builds up at the boundary, and that, as we said before, is an alternating current. So this alternating charge that's generated actually acts like another transmitter in addition to the main transmitter that's on the tool. So what you find is that you can get, it's almost like the signal gets boosted by the additional mini transmitters which are generated at these boundaries. And that means that the received signal at the tool can become distorted. And we'll have some examples of what that looks like coming up later on. Now here's quite a nice example of a boundary effect on the resistivity. The resistivity curves are shown in the right-hand track. I've just got two curves shown, shallow and deep resistivity. These are from the EWR Phase 4 tool. On the left, I've got gamma ray data, and the red curve there is the rate of penetration, the ROP. The important thing to notice here is that we've gone from a high resistivity formation. This is looks like a sandstone formation, probably a reservoir interval, and we've gone from that into a shale, which is higher gamma ray and lower resistivity. In fact, both sides of the reservoir section you have low resistivity shales, and we're crossing this interval at about 78 degrees inclination, so quite a high angle. And in that case, you generate, or you get these characteristic horns. These are called polarization horns, and they happen at the boundary, and they're caused by that build-up of charge, which I was just talking about, which happens as the currents in the tool are trying to cross that boundary. So what typically you see is that the deeper reading measurements have a larger effect. Here you can see that the deep resistivity has a very pronounced horn. The shallow doesn't really do very much. Coming out the other side, you do get a small horn on the shallow resistivity and an even bigger one on the deep resistivity. So this is a classic case. These polarization horns are very common in high angle wells, especially where we're crossing these high contrast boundaries between reservoir zones and adjacent low resistivity shales. Here's another situation which we sometimes encounter where a fracture exists in the formation which interferes with the measurement. Here we've got a piece of rock with a fracture penetrating it from the borehole. The fracture is filled with mud that may have a different resistivity from the formation. It could be higher or lower. What matters is that it's different. When the tool is measuring and generating these currents around the tool, it will behave in a similar way to what we had just now for the boundary case, where we get a buildup of charge across the fracture, which is going to interfere with the measurement. Looking closely at this, you can see there's actually like 2 mini boundaries associated with a fracture and 2 more on the other side. So it gets pretty complicated as to how this exactly affects the measurement. In practice, what you get is a spiky response on the tool or an erratic response when it goes past a fracture, and I'll show you some examples of that later on. Here's an example in which fractures in the well bore have had a significant impact on the log response. Don't worry about looking at all of the data on here. There's a lot of information on this plot. The main thing to look at is this track, which shows 4 resistivities, the 4 resistivities from the EWR Phase 4 tool. These are phase shift resistivities. And over on the right, I've got an image from the AFR, which is the azimuthal focused resistivity tool. That's a tool which I'll talk to you about later on in the presentation. But it can identify fractures in the borehole wall. This is an image of the borehole wall, and you can see these dark features showing up in the image, which are fractures. The borehole is heavily fractured in this area. And you can see that the result is that the Phase 4 resistivities are quite erratic. We have a lot of spikes and noisy looking data on those measurements, and that's caused by the presence of fractures. Remember in the previous slide I showed you how the fracture causes a polarization effect. That's what you're seeing here. So all this stuff through here that's very erratic and very noisy is mostly due to the presence of the fractures. Incidentally, the AFR tool itself, the one that made the images, also measures resistivity, and it does a much better job of seeing the true resistivity of the formation compared with the EWR, which is heavily influenced by the fractures. Again, I'll talk to you more about the AFR later on. Here's another situation that we sometimes see in which the tool is not centered in the borehole. This time it's off-center, it's laying on one side of the hole. And what happens in this case is that the borehole itself interferes with the current that's trying to flow around the tool. We've got the current here shown flowing around the tool, but it's having to cross a boundary between the formation and the borehole fluid. So that acts very similarly to the fracture or to the bed boundary case. You get a kind of polarization effect or a buildup of charge at this boundary, which is going to interfere with the measurement. Here's an example of an eccentricity effect on a resistivity log. On the left-hand side, I've got caliper data, the blue curve, which shows that we're in a pretty good gauge hole, very little washout. The black curve is the gamma ray, the red is the rate of penetration. On the right, we've got 4 measurements from the EWR Phase 4. The shallowest measurement is the green one, and the deepest measurement is the red one. Near the top and the bottom of this interval, the data doesn't look too bad. It's a little bit noisy, but it's not too bad. But there's an interval in the middle here which is extremely noisy. There are lots of spikes and lots of erratic behavior, which is very unlikely to be a true representation of the formation resistivity. What's happened here is the tool has been pushed off center as the drilling assembly is passing a dogleg, a turn in the well bore. The pink trace in the depth track here is the tool face. That's the tool face of the motor. When the motor is rotating, which is shown by this erratic looking curve here, that means that the well is basically going straight. But where it looks smooth like this, you get these periods where the curve is more or less constant, that's where we're actually steering and turning the direction of the well bore. So you can see that through this interval in the middle here, there was a short period when we were trying to steer the well. When the EWR tool came to that point, because there was a slight bend in the well, it was pushed off center. And because of the fact that in this case we had very low mud resistivity, I'm not sure exactly what it was, but it was very low. The fact that the formation resistivity is high, plus the mud resistivity is very low, that means that the measurement becomes very sensitive to eccentricity. and you get these erratic, spiky responses. Once we get clear of the dogleg and we get back into straight hole again, the log cleans up quite nicely. This is another situation that we find quite a lot in permeable formations, where the mud or the mud filtrate invades the formation, displacing the native fluids that were there to start with, and in doing so changes the resistivity of the rock. The borehole fluid obviously starts off like this, where there's no invasion, but then over time some of that fluid penetrates into the rock. And that's going to make a difference to our measurements, and in particular in cases where we have multiple measurements which have different depths of investigation. Longer spacings or lower frequencies will see deeper into the rock than shorter spacings and higher frequencies. So for example, we might have a shallow measurement which is seeing a zone which is heavily invaded. The medium measurement might be seeing a zone which is only slightly invaded, and the deep may still be reading a zone which is completely uninvaded. So that means that we're going to see a separation or a difference in result between the three measurements. Let's say this is a water-based mud, so it has a low resistivity relative to the formation. So the shallow measurement is likely to read lower because it's seeing more of the borehole fluid than the deep, which is still reading the native resistivity of the formation. Here's an example of how invasion affects the resistivity log. I've got data here again from the EWR phase 4. We have phase shift resistivity in this track and attenuation resistivity in this track. The black curves are the shallowest, the deepest is the red curve. On the left I've got a gamma ray and ROP curves. The interesting part is this part in the middle here where we've gone into a sand. We can see low gamma ray here indicating a sandier section compared with the intervals above, which are shale. In the shale we see very little separation between these curves. They're pretty much stacked on top of each other. In this interval there may be a small amount of borehole effect or possibly some anisotropy, but the main thing to look at is what happens in the sand. And here we're in water-based mud, and what that means is that the invading filtrate that's penetrating the formation has a lower resistivity than the formation fluid. Clearly there's a high resistivity zone here which suggests that it's hydrocarbon bearing, so the native resistivity is very high, and that's what the deeper measurements are reading. But the shallower measurements, especially the 9-inch phase resistivity, which is the shallowest measurement from the tool, are seeing some invaded zone. That's a zone where the wellbore fluid has penetrated the formation and displaced some of the oil that would have been there to start with. And that's brought down the resistivity close to the wellbore. And we get this characteristic spread, this separation of resistivity curves due to that process. You'll notice that on the attenuation data over here, there's much less of an effect. It's not nearly as pronounced as it is on the phase resistivity. In general, the attenuation data sees deeper into the formation and so will be less affected by the invasion process than the phase resistivity is. So these phase curves are the ones that are the most sensitive because the shallower ones are the shallowest measurements that the tool has, and they're the first ones that are going to see the invasion when it happens. The last effect that I want to mention for resistivity is anisotropy. Anisotropy is a property of the formation in which the measured resistivity varies depending on which direction you measure it in the formation. So you'll hear people talk about RH and RV, where RH is measured parallel to the bedding planes and RV is measured perpendicular to the bedding planes. Now the tool, if it's in a position like this where it's perpendicular to the bedding, is generating those loop currents which are looping around the tool, and those currents are flowing entirely within the thin beds. They're not crossing the boundaries between those thin beds. So they're just exposed entirely to RH in this orientation. But as the tool orientation changes, some of the current is now passing in the vertical direction. You can think of it as having two components now. The part of it is horizontal, part of it is vertical. And the more tilt there is in the tool, the more of that vertical component it's going to see. So let me show you what that looks like in terms of a log response. Here I've got a plot of relative dip versus resistivity. If you take the normal to the bedding plane, that is a line that's at right angles to the bedding plane, the angle between that and the borehole axis is what we mean by relative dip. So in this case we've got a 0 relative dip, and as we increase the inclination, the relative dip will also increase. And let's look at what the resistivity is going to do as the tool orientation changes. As it tilts over, we start off with low resistivities, which correspond typically to the RH component. But as we increase the relative dip, as we tilt the tool over, we see an increase in the resistivities. This is an EWR phase 4 example, but all of the tools behave in a similar way. So we see an increase, which means that the tool is seeing more of the RV component, which is the higher of the two resistivities. But it never actually reads entirely RV. Even when it's horizontal like this, the response is just a mixture of the two. Some of the current is seeing RH and some of it is seeing RV. The other thing that happens is that you see a separation between the measurements. You see that the two deeper measurements, the deepest and the medium spacing, they are almost the same, but they go quite high, whereas the shallower measurements don't respond as much. So on a log where you see that kind of separation with the two shallower spacings reading low relative to the other two, that very often is a signature of an anisotropic formation, which is a warning perhaps that the tool response is not reading a true measure of the formation resistivity. This is an example of a log where anisotropy has influenced the resistivity measurements. We're in a borehole where the inclination relative to the vertical is 54 degrees. We're in oil-based mud, and we're in a fairly small borehole. The fact that it's oil-based mud means that there is very little borehole effect, because oil-based mud has a very high resistivity. Looking at the log, you can see that we're in a shale based on the gamma ray response, which means we're unlikely to see any invasion. So with no borehole effect and no invasion, the only other explanation for the separation that we see between these curves is anisotropy. And because we're in a shale, shales are laminated, they're thinly laminated formations. It's typical to see this kind of spread or this kind of separation due to anisotropy in shale formations. In the EWR phase 4 in particular, there's this characteristic split where you have the 9 and 15-inch measurements separated away from the 27 and 39-inch measurements, which stack on top of each other. The reason they stack is because they're actually running at different frequencies, and the difference in frequency effectively cancels out the difference due to anisotropy. In cases where an anisotropic formation has been logged with a tool that has all the spacings running at the same frequency, some of our tools are like that, then you will see all the curves separate. You won't see the stacking taking place on the two deeper measurements. But in the phase 4, because of that difference in frequency, we get that stacking, and that's quite a useful indicator of anisotropy. Now this plot is a nice illustration for the kinds of effects that we might see on a log due to environmental issues. What we've got here is a plot from a deep water well. I think this came from the Gulf of Mexico, where we're drilling a 22-inch hole. That's a pretty big hole. And we see some pretty strange variation in our resistivity measurements. We've got phase shift resistivity up here and attenuation resistivities over here. And on the left we have the gamma ray curve. What I'd like you to do at this point is just pause the presentation and look at this plot and try to think of ways which might explain, or phenomena which might explain this. On first inspection, you can see there's a depth shift here, and that was, I think, in this case, the first thing that was noticed by the customer as to, something strange going on with this log. We seem to have a depth discrepancy. So if you pause the video and think about what might cause that, and then I'll come back later and explain what's going on. Okay, so I'll give you a little bit more information now about the situation that we're in. We're drilling with seawater. Seawater is used in top hole sections. It has a very light density, very low density, but it's also not very good at cleaning out the borehole. The viscosity of the water is pretty low, and it doesn't pick up the cuttings very well. So in these situations, from time to time, what the rig will do is pump what are called gel sweeps. That means that every now and again they'll switch from pumping seawater to pumping a much heavier, more viscous mud down the borehole, which will pick up the cuttings and effectively clean out the hole. So with that knowledge, I'd like you to pause the presentation again and think about how that might affect the logs and how it might explain what we're seeing. Okay, so hopefully you've managed to figure out what's going on here. We've got effects on both the gamma ray and the resistivity measurements. Let's look at the resistivity first. We've got some separation between the curves some of the time, and much less separation in other intervals. The separation of these curves is a borehole effect, and as I said before, the borehole effect is driven by the resistivity of the fluid that's in the borehole and also the diameter of the borehole. Now, it's a pretty safe bet that the diameter isn't changing so dramatically like this. What's actually changing is the pumping of these gel sweeps. So some intervals of the log have been recorded when there was seawater present in the borehole, and other intervals have been recorded when the gel sweep was being pumped. So what we're looking at here is a time-based effect. It's that things will change with time based on the changing mud system that's being pumped. So these intervals where there's a lot of separation, that corresponds to a fluid in the borehole that has a low resistivity. The lower the resistivity is of the mud that's in the borehole, the greater the borehole effect becomes, and it affects the shallowest spacings more than the deep spacings. This red curve is the deepest spacing, and it doesn't really change very much through all of this. It's pretty constant. So it's not really seeing much effect from the borehole or from the changing mud system, whereas the shallower measurements they're being affected quite dramatically by the change in the mud system. So here we've got a low resistivity mud, which is most likely the seawater, and then down here where we have much less borehole effect, the curves are almost in agreement, we have a higher resistivity borehole fluid, which will be the gel sweep, which is probably a freshwater gel, which has a pretty high resistivity relative to the seawater. So as we continue to drill, we alternate between seawater and gel as we go down the well, which causes this weird separation to come and go as we go along. Now, meanwhile, on the gamma ray curve, we have similar variation. We have high intervals and low intervals, and it looks at first glance like we have some kind of depth discrepancy between the two. But this is also an effect caused by the mud. The gamma ray sensor is slightly shallower in this case than the resistivity sensor. They're at different points on the drill string. So when, for example, we switch from seawater to gel at this point, the resistivity is at this point, at this depth. The gamma ray is at a slightly shallower depth. So the effect that we see on that happens at a slightly shallower depth. So they look like they're off depth, but they're not. What's happening is that both are affected in time by this time-based change in the mud system. The reason the gamma ray changes is because of the difference in density of these two fluids. The gamma rays, as I explained earlier, are attenuated by the fluid in the borehole. The attenuation is more for more dense fluids. So when we pump that viscous sweep, that 14 pound per gallon sweep, that attenuates the gamma ray measurement because its density is higher compared with the seawater, which has a lower density, and you see more gamma rays getting through. Now, if we were careful with our processing, we could correct for all of this. If we knew exactly what time the sweep or the seawater was reaching the tool, we could in principle apply corrections to bring all this into line. But in practice, that's nearly impossible, because to know exactly when a sweep reaches the tool downhole is very hard to do. We can't figure that out precisely enough so that we could do that. All we can do in this case is to explain what we're seeing and to explain to the customer that this is not actually a depth issue. We're not drilling through a sand shale sequence as you might expect from the gamma ray. This is simply a consequence of the gel sweeps that are being pumped, which is disrupting the measurements from both tools. Okay, just to illustrate a little more what's happening here, this is a little animation which illustrates what's going on. We're starting off by drilling in seawater. That gives us the separation that we've seen on the resistivity, and it gives us a particular response on the gamma ray. Notice the gamma ray sensor is actually lagging behind the resistivity sensor, which is a little deeper down the hole. At this point, we pump the sweep, and the gamma ray drops because the freshwater sweep has higher density and attenuates the gamma ray measurement, and has a higher resistivity as well, which removes most of the borehole effect from the resistivity measurement. As we keep on going, that alternates, and we see the same thing repeated over and over again as we go down the section. And it's all to do with the spacing between the gamma ray and the resistivity, and the fact that the environment that we're in is not constant. If you're used to looking at wireline logs, this is something completely new or different from what you've seen before. In a wireline environment, everything is constant. The mud is constant. There's no circulation. Nothing is changing. In an LWD environment, things can change with time. In particular, the mud properties can change with time. So it's important to think about the actual conditions in which the data is acquired when we're seeing behavior like this on logs. Otherwise, it's possible to misinterpret what you're seeing and come up with a completely wrong understanding of the situation. Okay, here's another example that I'd like you to spend a little time looking at and try to understand what might be causing the logs to change in the way they are. In this case, we've got a gamma ray curve on the left. We've got 4 resistivity curves on the right. The red is the deepest one and the black is the shallowest one. This is in an 8.5 inch hole. We've got a 6 3/4 inch tool. We're in quite heavy mud. It's 15.7 pound per gallon water-based mud with a fairly modest resistivity. It's not as low as it can be. 0.360 meters is kind of middle of the road. But we seem to have, once again, some kind of depth issue between the gamma ray and the resistivity. What I'd like you to do is spend a little moment and try to think about what might cause that kind of behavior on the log. Okay, hopefully you've had some time to think about that. What I'll do is try and explain what you're seeing. In terms of the drilling process, a lot of these strange looking logs come about because of the way the data was acquired, and I'll show that on the next slide. Okay, this illustrates what's going on in this situation. We're starting off drilling with the resistivity sensor below the gamma ray sensor. We get no separation to speak of between the resistivity curves, which suggests that there's very little borehole effect. At this point, the BHA was pulled out of the hole. We pulled out to change the bit, and that meant that there's a section of borehole here between the sensors and the drill bit, which hasn't yet been logged but has been drilled. Before we pulled out of the hole, we circulated mud to clean out the cuttings, and in doing so, that caused the borehole to become washed out, so enlarged. relative to the bit size. That meant that by the time we came back on the second run to continue drilling, the tools are now in a larger borehole than they were before. Now that has two effects. The first effect is for the resistivity to separate. We see separation between the four resistivity curves here. The shallower spacing drops down in resistivity because it's seeing a larger borehole and a larger borehole effect. Also, the gamma ray drops because it is now being attenuated more than it was before, because the gamma rays are now having to travel through more mud because we're in a larger hole, and the gamma ray response is suppressed. When we get back down to the point where the drill bit finished up the first time round, the separation on the resistivity more or less goes away. It's not completely, but most of it disappears, and the gamma ray comes back up. So this interval here on the gamma ray between this depth and somewhere here, the gamma ray response is suppressed, and that's not due to a change in formation, it's just due to a change in the hole size. And similarly from this point on the resistivity up to about here, again, that's not a change in the formation properties, that's a change in the borehole geometry. That needs to be understood so that we don't misinterpret this and think we're in something that we're not. Now, one way to catch this kind of thing is to plot something called the formation exposure time. The formation exposure time is the time between when a particular depth is drilled using the drill bit and when a particular sensor reaches that depth. So here I've got two formation exposure time curves. It's plotted on a I think it's a 0 to 40 hour scale, something like that, where the red curve is the exposure time for the resistivity and the green curve is the exposure time for the gamma ray. So the exposure time here is from when we're drilling the first time. You can see that the gamma ray exposure time is slightly higher because the gamma ray is lagging behind the resistivity and therefore takes longer to get to a particular depth after it's been drilled. At this point, this is where the gamma ray was when we pulled out, and this is where the resistivity was when we pulled out. So from that point down, the exposure time is large because this section of the hole was drilled a long time before we actually got around to logging it. And then down here, as we got back into the new hole, you can see it comes back in line. But plotting this exposure time alongside the regular curves can help us to understand what's going on. So you can see that there's a good correlation between, say, the resistivity exposure time here and the interval that's got the unusual separation. So that's a pretty good clue when we're looking at this to understand what it was that caused that separation in the resistivity, and the same thing going on the gamma ray. This suppressed interval corresponds with the interval of increased exposure time. So I would recommend plotting exposure time routinely. We do it routinely on resistivity logs because in general it has the greatest impact on resistivity logs. But in this case and in other cases, it also affects the gamma ray and it can affect other sensors as well. So it's a good diagnostic tool, and we should be plotting it on logs to help us understand what's going on. All right, now let's look at the different tool designs that we have in the field. We have three designs which basically do the same job of measuring formation resistivity, but they are all slightly different, and it's important to understand how those differences can show up on the logs. On the screen I've got the most basic design, the EWR Phase 4. This is our oldest tool that's still in service and provides the most basic measurements that we currently offer. This tool is what we call an uncompensated design, and I'll explain what that means in a minute. The picture shows the tool. This is the main tool collar with these striped bands which are transmitters and receivers. They're all antennas which are in rings around the collar. The four bands on the left, highlighted in red, are the transmitters. We have 4 transmitters, and we have 2 receivers shown in green. Now, You remember that I said before that to make a resistivity measurement you need two receivers and a transmitter. And we measure the phase shift and the amplitude ratio between the two receivers in order to get the formation resistivity. In this case, we have the two receivers and we also have 4 transmitters, and the spacing on these is important. The longer the spacing, that is the distance from the receiver to the transmitter, the longer that distance is, the deeper into the formation the measurement will read. Now you'll notice also that the frequency that we operate at is fixed on these 3 transmitters. It's all 2 megahertz. On the longest spacing it's 1 megahertz. We drop the frequency on that one just to push the depth of investigation a little deeper. Depth of investigation is dependent on frequency as well as spacing, and lowering the frequency helps to increase that depth of investigation on the deep spacing. The measurement point is defined as being the midpoint between the 2 receivers, and when you hear people talk about spacings, it's the distance between that measurement point and each of the transmitters. So, for example, the 9-inch spacing is the shortest spacing on the tool from the nearest transmitter to the receivers to the midpoint of the receivers. And we have 3 other spacings at 15, 27 and 39 inches. And the 39 inches is what we would call the deep spacing. This feeds the furthest into the formation, as I'm trying to illustrate on the cartoon here. And having multiple spacings like this is an advantage because it means that you can detect invasion in the formation. In the example I showed earlier about how invasion affects the measurements, in a case like this, you can typically see the native resistivity of the formation with the deep spacing, and maybe the shallowest spacing might be seeing some invasion, and the intermediate spacings will be somewhere in between. But having these multiple spacings is very useful for identifying invasion. Now, the uncompensated aspect of this tool, it simply means that all of the transmitters are on one side and the receivers are on the other side. The other tool designs I'll show you are what's called compensated design, which is a more advanced layout. This layout means that we have to apply some fairly complicated temperature corrections to compensate for errors in the receivers. The compensated designs, which I'll get to in just a moment, eliminate that. So this one is a little bit more prone to error, especially in larger or higher resistivity formations, compared with the compensated design. Okay, the next tool is the EWR M5. This is a more advanced tool than the Phase 4 that I showed you just now. The main differences between this and the Phase 4 are that it has, firstly, more spacings. It has 5 spacings rather than 4. Also, each of the transmitters on the tool operates at 3 different frequencies. We have 2 megahertz, 500 kilohertz and 250 kilohertz firings, which gives us a lot more measurements compared with the Phase 4 and a much wider range of depths of investigation. Now, the other thing about this is that it's what we call a compensated design. Now, compensated design really just means that you have a symmetrical arrangement of transmitters and receivers with a pair of receivers in the center and a transmitter on either side at equal distances from the receivers, so it's a symmetrical arrangement. What that does is gives you a reduction in the errors which exist, because you can essentially cancel out the errors by combining measurements from opposite sides of the receivers. Hopefully that will become a little clearer as we look at the tool layout. The bands on this tool are also antennas like it was in the other design. The ones on the right, the 3 on the right are transmitters, and the 3 on the left also are transmitters, and the 3 in the center are receivers. And you'll see why we need 3 receivers in a moment. Let's think about the first spacing to begin with, the shortest spacing. This will be the 16-inch spacing. Now here you can see we have a symmetrical arrangement. We've got R2 and R3 are the active receivers. We've turned off R1 for the time being. And T1 and T2 are firing, and they're symmetrical about the center. That means that the measurement from this side is combined with the measurement from this side, and the net result of that is that the measurements, or the resistivity measurement, gets amplified, whereas the errors in the receivers tend to be cancelled out. So it's a good way to reduce errors and to make the tool less sensitive to temperature changes. In the phase 4, as I said, we have to apply a fairly complicated temperature correction to compensate for drift in the receivers. In this case, any drift that we have in the receivers is automatically cancelled out by this compensated layout, so we don't have to worry about the temperature correction. So in order to get all those spacings, though, if we wanted to get, say, 5 spacings with a compensated arrangement like this, the first thought would be to put 5 transmitters on each side, and we don't have that in this case. What we have instead is a third receiver and some carefully chosen spacings so that we can maintain a compensated measurement. If we go to the next spacing, this is the 24-inch spacing. Here we've turned off R3 now. We've got R1 and R2 active, and T2 and T3 are again symmetrical with respect to those two receivers. So again, we can make a compensated measurement now at a longer spacing. And we can repeat that. We go back to the original pair, R2 and R3, for the 32-inch spacing, and then the 40-inch spacing and the 48-inch spacing. So this provides 5 compensated measurements, but with fewer antenna on the tool than you might otherwise expect. In a conventional layout, you might have 2 receivers and then 5 transmitters on each side, which makes for a lot of antennas. In this case, by adding the extra receiver, we can cut down on the total number of antennas that we need, which keeps the cost of the tool down. Okay, the M5 design, in addition to being compensated, also has a number of other advantages over the Phase 4. Most of those come from the use of lower frequencies on the tool. As well as the 2 megahertz, which we use in the Phase 4, we also use a 500 kilohertz and a 250 kilohertz firing. And that brings several advantages. We have a greater depth of investigation. Generally speaking, low frequency measurements will see deeper into the formation than higher frequency measurements. And that's advantageous if you have invasion and you're trying to see the true resistivity beyond the invaded zone. There's also a problem which exists with the high frequency data when we're in oil-based mud, which is very resistive, and we're in a low resistivity formation. That produces a very high contrast in resistivity between the borehole and the formation, and that then makes the measurement very sensitive to tool position. So if the tool is eccentered or off-center in the borehole, that can cause spiking on the log, which I'll show you an example of in just a moment. Polarization horns, those happen around bed boundaries. I mentioned earlier about the fact that bed boundaries can interfere with the measurement. They show up as high resistivity values around the boundary, which we call a polarization horn. If you use a lower frequency, the effect of those is much reduced. They're not eliminated altogether, but they are reduced. Another couple of benefits. One is reduced dielectric effects. The formation resistivity is only one property that the formation has that this tool is affected by, the other being the dielectric properties of the rock. The advantage of using a low frequency is that the dielectric effect is much less, and the resistivity is the predominant mechanism that controls the measurement. So in some cases where we have formations with unusually high dielectric properties, using a low frequency measurement can help. Anisotropy also affects our measurements. I showed you an example of what that looks like earlier on. By reducing the frequency, we can also reduce the effect that the anisotropy has on the measurement. Now, we don't just stick with low frequencies, though. We still keep the high frequency data. Mostly that's because it's more accurate in thinly laminated zones. It has a better vertical resolution, so it's able to pick out the thin zones more effectively than a low frequency measurement would be. It's also better at picking out the invaded zone. The RXO is the flushed zone resistivity, and we get a better result from the high frequency data if we want to try to measure that. That's an important parameter for the petrophysics analysis of the reservoir. Now, this is an example of that problem I mentioned where we are running in oil-based mud and the formation resistivity is very low. This plot shows the 2 megahertz data. On the left, we've got the phase resistivity, and on the right, we've got the attenuation resistivity. The attenuation looks a little better, but the phase resistivity is very spiky. In fact, they're both pretty spiky. You can see that the resistivity is, well, it's hard to see what the resistivity is doing really because of the spiking. In fact, we do have a very low resistivity, but it's hard to see that through all the spikiness. So if we go to lower frequency, this is a 250 kilohertz, this is over the same interval, you can see a much cleaner looking log. We don't get any of the spiking and we get a very clear picture of the resistivity. You can see we're going down very low here. We're going down to less than 0.2 ohm meters, which is unusually low, but as I said, in places like the Gulf of Mexico, that's not very uncommon. That happens quite a bit. And so in order to avoid the spiky problems that we get with the high frequency firing, we use a low frequency measurement which gets rid of all of that. Now the third tool I want to show you is our latest tool for resistivity measurements, and that is the ADR, the azimuthal deep resistivity. In some ways this is similar to the M5, although we don't have as many spacings on this tool. It only has 3 spacings rather than 5. But it is a compensated design, but it is also azimuthal. That is, that the measurement, rather than making an average resistivity measurement from all directions around the borehole, actually is sensitive to just one side of the hole. So as the tool rotates, it effectively can scan around the borehole, producing an image, but more importantly being able to distinguish between resistivities in different directions around the wellbore. And this comes in very useful when we're trying to do geosteering, where we're trying to detect approaching boundaries. If we're in a high angle well, a horizontal well say, and we're trying to detect boundaries above or below the well, then the ability to tell the direction of those boundaries relative to the wellbore is extremely important for the point of view of geosteering. So this tool, it's laid out as shown in the picture. We've got 3 transmitters on either side of these 2 tilted receivers in the center. It's the tilt on those, they're at 45 degrees to the tool axis. It's that tilt which gives the tool its azimuthal sensitivity. We also have another receiver down here, and I'll explain what that's for as we go on. That doesn't make a resistivity measurement, it makes what we call a geosignal measurement, and that's the primary measurement that we use for geosteering. So each of these transmitters fires at 3 frequencies. It's almost the same as the M5. We have 2 megahertz and 500 kilohertz. The lowest frequency was dropped from 250 to 125 when we designed the ADR. Again, that was just to boost the depth of investigation. For a geosteering tool like this, it's very important that it can see as far into the formation as possible, so we get the earliest warning of approaching bed boundaries. So we pushed the frequency down as low as we could to help with that. But otherwise it works on the same principles of phase and amplitude measurements that I described earlier on. If you add up all the different combinations and permutations of spacings, frequencies, plus the azimuthal binning, that the tool divides up the azimuthal measurements into 32 sectors around the borehole, that gives us an enormous amount of information with which to make geosteering decisions. We don't, of course, just give the customer 1,000 measurements and expect them to understand what they all mean. We combine them and present them in our geosteering software to make sense of it and to display geological models and so on in the geosteering software. So you can think of the ADR as being two tools in one. It provides resistivity measurements, which is what the customer's petrophysicist is interested in, and it also provides deep geosignal measurements, which we use for geosteering. I'll take you through the differences between the two parts of the tool. The resistivity part is centered around the two receivers in the center, these two tilted receivers, and we get three compensated resistivity measurements from there. We get a 16, a 32, and a 48-inch spacing, which are three of the same spacings that the M5 tool had that I was talking about a moment ago. From these spacings we get resistivity, of course. It's average resistivity like the M5, but also azimuthal resistivity, which means that it's measured in different directions around the borehole. Each of those spacings operates at multiple frequencies. The 2 megahertz and 500 kilohertz firings run on all spacings. The 125 kilohertz firing runs only on the 48-inch spacing. Each of those also provides phase and attenuation measurements in the same way that the other tools do, to provide a very wide range of measurements from very shallow to very deep, to give you a lot of different depths of investigation to help characterize, for example, an invaded zone in a reservoir. The deeper measurements will give you RT, the true formation resistivity, and we also use resistivity for fine-tuning our geosteering. Once we get close to bed boundaries, for example, if we want to maintain position relative to the top of a reservoir, close to a shale, for example, we can use the resistivity measurements, which don't see all that deep compared with the geosteering measurements. We can use those relatively shallow measurements to fine-tune our tool position relative to that boundary. The other aspect of the ADR is the geosteering capability, and most of that is driven by the deep receiver, this R3 receiver shown on the diagram. This is a measurement which is called a geosignal. It's not a resistivity measurement, and it's a little bit complicated as to exactly what a geosignal means, but one way to think about it would be that it's simply a measure of the phase or amplitude of a single signal from one of the transmitters. And we compare the phase on one side of the tool with the phase on the other side, or the amplitude on one side versus the amplitude on the other side. We take the difference or the ratio between those and call that a geosignal. In a geosteering environment, that's very useful because that has two things about it. One is that it is very deep reading, and the other is that as we approach a boundary, suppose there's a boundary above the tool, the measurement on one side of the tool will change relative to the measurement on the other side. So the geosignal value that we get, which is the difference between them or the ratio between them, will also change. And we can use that to help us determine how far away we are from the boundary. Now the measurements we actually use on the tool are these long spacing measurements, the 80, 96 and 112-inch spacings. These are not going to give you a resistivity. These are only going to give you the geosignal. But these are the primary measurements that we use for geosteering. They're azimuthal, which means we get a value in all directions around the borehole. We run this at the lower frequencies. We don't bother with the 2 megahertz because that's too shallow reading. We just use the 500 kilohertz and the 125 kilohertz firings for the deep geosignals. But we do get phase and attenuation geosignals, both of which are used by our geosteering engineers when they're steering the well. And this gives us a very deep depth of investigation. The deepest measurement comes from the longest spacing, this 112-inch spacing, running at 125 kilohertz from the attenuation measurement. That combination gives us the deepest spacing, deepest measurement, which goes out to about 18 feet from the borehole. And that is the one that's going to be the first to detect bed boundaries as we approach them, and which is the most useful when we're geosteering, because very often we don't want to cross those boundaries. We want to maintain position within a reservoir and avoid exiting through the top or the bottom boundaries. And the other thing that we can get from this is actually a quantitative measure of the distance to those boundaries. Not simply that the boundary is there, but how far away it is. We can calculate a distance in feet or meters from the borehole to a nearby boundary using the information that's contained in these geosignals. This slide tries to illustrate the importance of azimuthal resistivity when we're talking about geosteering applications. This is a model showing resistivity in two layers. We have an 18 ohm-meter formation, which could be a shale, for example, and we have a higher resistivity below. We've got 40 ohm-meters down here. This could be the reservoir, for example. And we've got a well path which is moving up through the reservoir, crossing the boundary and into the shale. Up here we've got resistivity values from an upward facing and downward facing component of the measurement. The black trace in the middle is the average resistivity. That's what you might expect to see if you ran a conventional tool like the M5 or the Phase 4. You would see a slight change at the boundary, but you wouldn't see very much. Whereas the up and down facing curves, they separate. And it's that separation between the curves that will tell you that there is a boundary approaching. So you can see that separation starts way back here before we actually reach the boundary. So in this area here, where the separation is increasing, you can see that and you can react to it and potentially steer the well away from the boundary based on that information. But if we go all the way through the boundary, what you see is a peak on the downward facing measurement. Typically the one that goes highest will be the one that's facing the higher resistivity. So in this case, you've got RT down here is the higher resistivity. So the downward facing measurement will peak high, whereas the upward facing measurement stays pretty flat and simply gradually drops down to the resistivity of the shale. We also display the data as an image, which is shown at the top, where we've got high resistivity values shown as the yellow color and lower resistivities as a brown. And by plotting the azimuthal measurements as an image, you see this kind of bright spot behavior around the boundary. That's characteristic of the boundary. Some people like to look at images, some people like to look at curves, but they're essentially showing you much the same thing. And it's this type of information and this type of display that we use for our geosteering decision making. This is an example from a real well where we're approaching a boundary from below. I've got a number of measurements on the screen here. We have average resistivity in this track. We have up and down resistivities from the azimuthal part of the tool, and these geosignals which are shown in the third track. We also have the geosignal shown as an image, and at the top we have a density image which comes from the ALD density tool. I'm going to talk about that later on. The important thing to notice here though is the amount of warning that you get as you approach the boundary. The boundary is here. This is where the density is crossing the boundary here, where we see a change from low density to high density. But before we get there, some of these other signals are starting to react. All the way back here, we start to see separation between the up and down facing geosignals. And the closer we get to the boundary, the greater that separation becomes until it becomes very large as we actually get to the boundary itself. Below that, we get the up and down resistivity. Remember I said that doesn't see as deep into the formation, so it doesn't respond as early to the boundary as the geosignal does. So we don't really see any separation until around here somewhere. But then as we approach the boundary, we do see a dramatic response where it goes off scale here. That's a polarization horn effect, where the downward facing resistivity in this case, which are the two brown curves, is horning. It's going high. The upward facing, which is the blue curve, doesn't respond as dramatically. Down here we've got the average resistivity, which really doesn't do anything at all until we get very close to the boundary. We see some slight separation here before we go through the boundary. So what this is meant to illustrate is the value of the geosignal data. It gives us a very early warning relative to the other measurements. If you put some numbers on this, it's about, in this case, 58 feet prior to the boundary. penetration, we actually start to see some separation in the geosignal data. That's 58 feet measured depth along the borehole. In practice, that's actually a fairly short example. We often see cases where we may see many hundreds of feet early warning before the boundary is actually penetrated. It all depends on the angle of attack. If the lower the angle between the wellbore and the bedding plane, the more warning you're going to get that that boundary is approaching. If you compare that with the azimuthal resistivity measurements, we only get about 19 feet or so warning there. And on the average resistivity, it's even less. It's maybe 5 feet or something like that. Now, something I said earlier about anisotropy was that it can interfere with the measurement. But we can actually turn that round and make use of that interference to calculate or quantify the anisotropy in a formation. In a laminated reservoir, the resistivity that you measure depends on the direction that you measure it. So on this picture, we've got a laminated formation where you have RH, the horizontal component, or rather the component measured parallel to the bedding, and RV, V stands for vertical. What it really means is perpendicular to the bedding. The bedding itself doesn't have to be horizontal for that to apply. So we have RH, we have RV. Those are different resistivity values that you get depending which direction you measure the resistivity. Typically RV is higher than RH. If we know those things, we can then derive resistivities for the sand layers which are contained within this sand shale sequence. The FRS group has software which will take these inputs and calculate that sand resistivity. And that's really the thing that the petrophysicist wants to know, so that they can do a proper evaluation of the hydrocarbon bearing zones, which are just going to be the thin sands, not the shales. Now the ADR is quite good for this, because what we can do is we can take all the different measurements from it, each of which is going to be affected differently by the anisotropy, and we can back out the RH and RV values from those measurements, provided the ADR is more than about 35 degrees relative dip to the formation. So just to remind you, relative dip means 0 relative dip would be perpendicular to the bedding in this direction, 90 degrees would be parallel. So the ADR would have to be at about 35 degrees or more relative to the bedding in order to be able to get a reliable measure of anisotropy. Sperry has software which will take the raw measurements and calculate RH and RV, and then we can calculate from that, using FRS applications, what the actual reservoir properties are. We can get anisotropy from the other tools as well, but you have to be at a higher angle for it to work reliably. You need to be at least 70 degrees relative dip with the phase 4 and the M5 in order to get a reliable anisotropy measurement. Here's an example log from a laminated formation. We've got a density image on the left-hand side. We've got images from the ADR here. From this data from the ADR, we can calculate the RH and RV, the horizontal and vertical, parallel and perpendicular components of the resistivity. And in addition, we also get a value of the relative dip. So the blue curve that's shown on the right-hand side here is an indication of the relative dip. I think we're on a scale of 0 to 100 degrees in this case. Now, dip, of course, can also be calculated from the borehole image, the density image. These sinusoidal features, the blue lines, are pics of the boundaries, and the amplitude and position of those sinusoids can be used to calculate the dip of the bedding planes that are cutting across the borehole. And those are shown as tadpoles on the right-hand side. The red head of the tadpole, its position from left to right, indicates the dip angle of the formation, and the tail indicates the compass direction in which it's dipping. So you can see that the dip calculated from the density image overlays pretty well with the dip from the ADR. So we have two different ways. If we're in a laminated formation, we can get dip from the ADR data, or we can get dip from the density. Bear in mind, though, that for ADR you have to be at a high enough angle, over about 35 degrees, in order to get reliable data for this kind of application.